Dr. Anthony Raj. He has pursued his bachelor's, master's and MPhil in physics. He then went on to pursue his PhD in physics at the University of Madras as well. He then went on to work as a lecturer at Thiruvalluvar Arts and Science College and Idea Engineering College for Women. Since the year 2006, he works as the lecturer and assistant professor at Loyola College, Chennai. With regard to research, he has published several papers in international journals, namely Radio Wave Propagation over Salem, Linear and Non-Linear Optical Properties of Pure and Doped Selenium Malate Single Crystals, and many more. He has also attended several conferences and seminars, namely International Conference on Materials Science and Technology, National Conference on Higher Education at Crossroads held at Loyola College, National Seminar on Crystal Growth 12 held at VIT University, and many more.
Welcome to UGC lecture series BSc Physics Honours Mathematical Physics 2 Semester 2 Lecture 9. In this lecture, we are going to learn about particular integral. This particular integral is a part in the solutions of non-homogeneous linear differential equation. This particular integral can be obtained by variation of parameter. We are going to learn this method, then method of undetermined coefficients, then summary. These are all the topics we are going to learn in this lecture. Particular integral. The solution of non-homogeneous equation consists of a complementary function and particular integral. We know that. So, there are many methods for determining a particular integral of a linear differential equation with constant coefficient. Out of those methods, in this lecture we are going to discuss the variation of parameter and method of undetermined coefficients. These are the two methods we are going to learn. Variation of parameters. From the complementary function of the solution of non-homogeneous differential equation, we obtained an equation like this, that is y is equal to c1 into y1 of x plus c2 into y2 of x plus etc. plus cn yn of x, where this c1, c2, cn are all arbitrary constants. This equation shows the linear combination of the solutions of non-homogeneous differential equation. This is the complementary function part of the solution of non-homogeneous equation. From this solution, we obtain a basic relation, that is y is equal to L1 of x into y1 of x plus L2 of x into y2 of x plus etc. plus Ln of x into yn of x. This is the basic relation we obtain from the complementary function of the solution of non-homogeneous differential equation. In this, we just replaced the c's by an unknown function of x, the L's. This is what we did in this equation. So, that is we are varying the parameter of the complementary function. By this we can find the particular integral of the non-homogeneous particular integral of the solution of non-homogeneous differential equation. The method consists of a procedure for determining the L's, so that equation 2, which consists the L, satisfy the non-homogeneous differential equation. We know the general form of non-homogeneous differential equation. So, this is the variation of parameter method to obtain the particular integral of the solution of non-homogeneous differential equation. Now, procedure to determine L's. From the complementary function of the solution of non-homogeneous equation, we got y is equal to c1 into y1 of x plus c2 into y2 of x plus etc. plus cn into yn of x is the complementary function part of the solution of the non-homogeneous differential equation. Keep this as equation 1. Now, what we need to do is we have to show that if y is equal to C1 y1 plus C2 y2 plus C3 y3 is the complementary function of the equation f of d into y is equal to d cube plus p1 d square plus p2 d plus p3 into y is equal to q. This is the first thing we need to do to get the L's. So, we need to show that y is equal to C1 y1 plus C2 y2 plus C3 y3 is the complementary function of the non-homogeneous linear differential equation given like this. Then we get y is equal to L1 y1 plus L2 y2 plus L3 y3. So, this is in this equation we introduced a parameter L1 by replacing the c's exist in the complementary function. Let us keep this as equation 1. Now, this L1, L2 and L3 must satisfy the following condition. The conditions are L1 prime y1 plus L2 prime y2 plus L3 prime y3 is equal to 0. This is the first condition to be satisfied by this L1, L2 and L3. Then the next thing is L1 prime y1 prime plus L2 prime y2 prime plus L3 prime y3 prime is equal to 0. Then the third condition is L1 prime y1 double prime plus L2 prime y2 double prime plus L3 prime y3 double prime is equal to q. These are the three conditions to be satisfied by the assumed parameter L1, L2, L3. Let us keep these as a set of equations A. So, this is a particular solution of the differential equation. In view of A, by successive differentiation of this equation, that is y is equal to L1 y1 plus L2 y2 plus L3 y3, by successive differentiation of this, we obtain dy is equal to L1 y1 prime plus L2 y2 prime plus L3 y3 prime plus L1 prime y1 plus L2 prime y2 plus L3 prime y3. So, in the conditions we learnt that this L1 prime y1 plus L2 prime y2 plus L3 prime y3 is equal to 0. L1 prime y1 plus L2 prime y2 plus L3 prime y3 is equal to 0. So, this one will become 0. So, we get dy is equal to L1 y1 prime plus L2 y2 prime plus L3 y3 prime. So, this is how we get that d suffix y. Now, differentiate this dy once again. So, we get d square y which is equal to L1 y1 double prime plus L2 y2 double prime plus L3 y3 double prime plus L1 prime y1 prime plus L2 prime y2 prime plus L3 prime y3 prime. So, this is also equal to 0 according to this condition. L1 prime y1 prime plus L2 prime y2 prime plus L3 prime y3 prime is equal to 0. So, this part will become 0. So, we get d square y is equal to L1 y1 double prime plus L2 y2 double prime plus L3 y3 double prime. Now, go to d cube y. So, d cube y is equal to differentiation of this equation once again with respect to y. Now, we will get L1 y1 triple prime plus L2 y2 triple prime plus L1 prime y1 double prime plus L2 prime y2 double prime plus L3 prime y3 triple prime. So, this is the equation we obtain after differentiating this d square y with respect to y. Again applying the condition, we get L1 y1 triple prime plus L2 y2 triple prime plus L3 y3 triple prime double prime plus q. So, this is the final expression we got. Keep all these equations as set B. So, the conditions set A and the conditions set B are fixed to obtain the particular integral. Then that f of d y will be equal to L1 into y1 triple prime plus p1 y1 double prime plus p2 y1 prime plus p3 y1. So, then plus L2 into y2 triple prime plus p1 y2 double prime plus p2 y2 prime plus p3 y2 plus L3 into y3 triple prime plus p1 y3 double prime plus p2 y3 prime plus p3 y3 plus q. This is how this f of d into y will become after substituting the conditions A and B. Now, the final thing will be is equal to L1 f of d into y1 plus L2 into f of d into y2 plus L3 into f of d into y3 plus q. This is how the final expression for f of d into y will become. Now, we know that this L1 f of d into y1 is equal to 0, then L2 f of d into y is also equal to 0, then L3 f of d into y3 is also equal to 0. So, we get 0 plus 0 plus 0 plus cube. So, the y1, y2, y3 are y1, y2, y3 are solutions of f of d into y is equal to 0. So, this is how the L can be obtained for the variation of parameter. So, in using this method, that is method to find L, we first write the complementary function, then form the L function given by equation 1, that is y is equal to L1 y1 of x plus L2 y2 of x plus L3 y3 of x. Like that, we need to form the L function, which is to be a particular integral by replacing the c's of the complementary function with L's, then obtain equation B by differentiating equation 1 as many times as the degree of the differential equation, then set the sum of all terms containing derivatives of the L's equal to 0, except in the case of last differentiation when the sum is set equal to 0. Then the equation obtained by setting the sums equal to 0 and Q are equations A, solve the equations for L1 prime, L2 prime, etc. Obtain the values of L1, L2, etc. by integration. We will get particular integral for the given non-homogeneous differential equation. So, using this method, we can follow these steps to find the particular integral. Now, we will do an example to understand the concepts we learned in finding the particular integral. The equation given here is example given here is solve d square minus 2d into y is equal to e power x sin x. This is a non-homogeneous second order differential equation. So, solution of this differential equation consists of a complementary part and a particular integral. We will be using the variation of parameter method to find the particular integral of the solution of this equation. So, solution to this equation will be first find the complementary function. So, the complementary function is y is equal to C1 plus C2 e power 2x, where this d square minus 2d is factorized and we got roots. That roots are substituted to get this complementary function. Now, using this complementary function, we need to find the parameter L to obtain the particular integral. So, we form the relation y is equal to L1 plus L2 e power 2x. As we learnt earlier in the theory that c's are replaced by the unknown parameter L, then this is differentiated as many times as the order of the differential equation. So, differentiate this y. So, the first differentiation dy gives 2 L2 e power 2x plus L1 dash plus L2 prime into e power 2x. So, and set this L1 prime plus L2 prime e power 2x is equal to 0. This is one of the condition. L1 prime plus L2 prime e power 2x is equal to 0. So, the dy will become dy is equal to 2 L2 e power 2x. This is the first derivative of the given L function. Next, we need to differentiate this once again, because order of the differential equation is 2. So, 2 times it should be differentiated. So, d square y is equal to 4 L L2 into e power 2x plus 2 into L2 prime e power 2x, and we set this 2 into L2 prime e power 2x is equal to q. Now, set this 2 into L2 prime e power 2x is equal to q. The value of q in this equation is e power x sin x. So, this is equal to e power x sin x. Thus, L2 prime is equal to 1 by 2 e power minus x sin x. So, L2 prime is equal to 1 by 2 e power minus x sin x. Now, integrate this, you will get the value of L2. So, L2 is equal to minus 1 by 4 e power minus x into sin x plus cos x. This is the value of L2. Now, from 1 that L1 prime is equal to minus L2 prime e power 2x, which is equal to minus 1 by 2 e power x sin x, and L1 is equal to minus 1 by 4 e power x sin x minus cos x, e power x sin x minus cos x. This is the value of L1 prime. This is integrated, we get the value of L1. So, a particular integral of the given equation is y is equal to L1 plus L2 into e power 2x, which is equal to minus 1 by 4 e power x sin x minus cos x minus 1 by 4 e power x into sin x plus cos x. So, by simplification we will get minus 1 by 2 e power x sin x. So, y is equal to minus 1 by 2 e power x sin x. This is the particular integral of the solution of the given non-homogeneous differential equation. So, the complete solution of this non-homogeneous differential equation is y is equal to C1 plus C2 into e power 2x minus half into e power x sin x is the complete solution of the given differential equation. Complete solution of the given differential equation d square minus 2d into y is equal to e power x sin x. So, from this problem what we learnt is how to apply the first method, that is method of variation of parameter to get the particular integral of the solution of the given differential equation. Then the next method to determine the particular integral is undetermined coefficients. The basic relation here is y is equal to a r1 of x plus b r2 of x plus c r3 of x plus etc. plus g rt of x is a basic relation. In this basic relation, the functions r1 of x to r2 of x are the terms of q, and those arising from these terms by differentiation, and a, b, c etc. g are all constants. So, this is the method of determining the particular integral by undetermined coefficient. This undetermined coefficient method to determine the particular integral can be understood more clearly by the following example. If the equation is f of d into y is equal to x cube, then we take for y is equal to ax cube plus bx square plus cx plus d. So, if the given equation is f of d into y is equal to x cube, then the function, the basic relation here is a x cube plus b x square plus c x plus d. If the equation is f of d into y is equal to e power x plus e power 3x, we take for 1 y is equal to a e power x plus b e power 3x. So, this is how we need to set the given function if the given differential equation is like this. Now, new terms are obtained by differentiating this e x and e power 3x. So, the new terms are obtained by differentiating this e power x and e power 3x. So, if the equation is f of d into y is equal to sin ax, we take y as a sin ax plus b cos ax. So, this is how we need to set the function for different equation. So, here the basic relation is y is equal to a r1 of x plus b r2 of x plus c r3 of x plus etc. plus g rt of x, where the terms of q and those arising from this term by differentiation and a, b, c, etc. g are constant. If the equation is f of d into y is equal to x cube, then the basic relation to be set is y is equal to ax cube plus bx square plus cx plus d. Then, if the equation is f of d into y is equal to e power x plus e power 3x, then the basic relation to be set is y is equal to a e power x plus b e power 3x, where this e power x and e power 3x are differentiated. Then, if the equation is f of d into y is equal to sin ax, then the function to be set is y is equal to a sin ax plus b cos ax. This is how we can set the function to determine the particular integral using the undetermined coefficients. So, from this lecture we learnt the procedure to obtain the particular integral. We know that particular integral is a part in the solution of a non-homogeneous differential equation. The particular integral can be obtained by two methods. We learnt both the method in this lecture. The first method is variation of parameter. In this method we replaced the c1, c2, c3 etc. in a complementary function by a parameter L. So, after solving that we obtain the value of L. That L is the particular integral for the solution of the given differential equation. Then the second method is undetermined coefficients. In this undetermined coefficient method, particular integral is obtained by fixing a relation from the given equation. These are all the concepts we learnt from this lecture. After listening to this lecture, you can answer the following questions. First question is define non-homogeneous differential equation. Then second one, what do you mean particular integral? Third one, solve the given differential equation d square plus 4 into y is equal to x square sin 2x. Thank you.